global warming, greenhouse gases, and then we'll see other properties. Okay. So what is the refrigerant selection criteria? Selection of refrigerant for a particular application is based on following requirements. So we are going to study three criteria in the selection of refrigerant. First is thermodynamic and thermophysical properties. So this will include your viscosity, specific heat, and all those thermal properties, thermophysical properties. Second is environmental and safety properties. So in this environmental and safety properties, we'll study ozone layer, ozone depletion, global warming, and why some refrigerants are nowadays are banned because of this ozone depletion. And in safety, we'll see like the toxicity and flammability of some refrigerants. Okay, so ASHRAE is providing standards in that safety of refrigerants. Okay, in last lecture I have told you, ASHRAE standard 15 it provides guidelines for handling of refrigerants, and ASHRAE standard 34 it gives guidelines in like nomenclature of refrigerant. So how this how these refrigerants will be classified and how this numbering works. Like we have R11, R12, R22. How this numbering is given. So that is specified by ASHRAE standard 34. And third criteria is economics. Yes. So even though you select the best possible refrigerant, under the economic consideration, it also hold good. So if you are creating a bill of material for suppose a chill water system plant, central air conditioning plant, in that bill of materials you are adding how much amount of refrigerant will be required. So that refrigerant should be easily available and its cost should be fair. I won't say it should be minimum, but it should be fair. Okay. So what you see on the left, so I'll start this laser. So what you see here on the right, that is a diagram for ozone layer depletion. So I'll first ask you what is the function of ozone layer? So can anybody answer that? So we all are hearing about ozone layer. So ozone layer is present in the stratosphere about 30 kilometers from our Earth's surface. And we have been studying from our school days that ozone layer is very important. So anybody knows why ozone layer is important? Yes. So I have one answer. Others, please participate. This is a very GK question. Like, what is the function of ozone layer? So we have ozone layer around the Earth in the stratosphere. So what is the function of it? Okay, so I have three answers here. Rohit said to absorb UV rays, Pranil restrict the harmful rays, and Sunil says introduce the intensity of ET rays, I don't know what IT rays. I have heard for the first time there are IT rays. So Rohit, you are saying to absorb the UV rays. Okay, Sunil, it is UV rays. Okay, I agree that they absorb the UV rays, but why we are we don't want UV rays? Okay, so I agree that ozone layer absorbs the UV rays, but what is the harm in getting UV rays? Okay, so I have one answer. They are harmful for living things. They can cause skin cancer. So not only human beings. So for human beings, it is true that they can cause like longer exposure of UV rays. So there are three types of UV rays. So currently, I'm working one project in our college, like a UV disinfection box. In that time, I came to know there are three types of UV rays. So UVA, UVB, and UVC. Uh, yes, they are harmful for a human. They can cause skin cancer, but not only humans, they are harmful for crops also. So whatever crops in our farm fields, they are it is UV rays are harmful to them also. So for that we don't want UV rays. So ozone layer is very important. It absorbs that UV rays. And what is happening actually? So whenever that VCRS was invented back in 1920, there that time they were using refrigerant. So first they were using air. So we studied the air refrigerant system. Then they were using water for refrigeration, and later they started producing the synthetic refrigerants in labs because that the temperature requirement was very low, like below 0 degrees Celsius. In that case, they needed a heat carrying medium which can work very smoothly under this minus temperature conditions. So they manufactured these refrigerants in labs, and everything was very good and everyone was very happy. So they were using ACs in 1960s, 70s. But what happened after that? A study was conducted in the space station that they were studying this ozone layer in the space from the space, and they observed that there were some holes created in that ozone layer. And after that, research was carried out, like what is the cause of this ozone depletion? Why these holes are created in the ozone layer? So it was observed that chlorine and bromine are very they are playing very important role or the major role in the depletion of ozone. So a summit was conducted. So that summit is called a Montreal Summit. It was conducted in 1987. So various nations under United Nations, they participated in it, and they decided that they will stop the production of the refrigerants, which involve chlorine. Okay, so in that summit, it was decided. After that, various refrigerants like R11, R12, they were stopped. The production of this refrigerant was stopped. Okay, so it is very important that we should study this ozone depletion when we are studying about refrigerants. Okay, so first I will start this thermodynamic properties. Then we can go for environmental uh, and safety properties. Okay, so thermodynamic and thermophysical properties that will start now. Let me connect my tab. Okay, first property we study, that is suction pressure. Suction pressure, as we know, that is evaporator pressure, and discharge pressure, that is a condenser pressure. So suction pressure, what it says. So at a given evaporator temperature, the saturation pressure should be above atmospheric for the prevention of air or moisture and non-condensable gases ingress into the system and ease of leak detection. Higher suction pressure is better as it leads to smaller compression displacement. So this I will explain with the help of pH chart. So we have pressure versus enthalpy charts that we have studied previously. Okay, so we have the saturation liquid curve, saturation vapor curve, and then we have here somewhere critical point. So in last lecture also, I have told you that refrigerant should have high critical point and low freezing point. So that will I will explain again today. So I will draw one VCRS cycle. So this is 1 to 2 compression, 2 to 3 condensation, 3 to 4 again isenthalpic expansion, and 4 to 1 is evaporation. So what it's saying that whatever suction pressure here, this suction pressure, this is a pressure, evaporator pressure, and then we have a discharge pressure, that is a condenser pressure. So that is saying that this evaporator pressure should be above the atmospheric pressure. Okay, so that means that if I take pressure here, one more pressure I am taking here, one more pressure below the evaporator pressure. Okay. Now we have two cases. Our atmospheric pressure is higher than evaporator pressure, and one is below the evaporator pressure. Let us say this is P1 and P2. So what happens when the atmospheric pressure is higher? Suppose there is this refrigerant tube is there, inside which the refrigerant is flowing. Okay, so it is flowing in this direction, and inside pressure is evaporator pressure, that is a PE. Outside pressure is P1, which is a P1 which is greater than PE. So what will happen in that case? This will form a vacuum because it is a less than the atmospheric condition. So the external pressure will be generated on the tubings. And if there is any crack in the tubing, what will happen? The outside air, outside moisture, that will go, or in general we call it as infiltrate. So it will infiltrate inside the tubing, and it can lower the performance of the system. If I take the another case, in that case, the pressure outside, that is P2, which is a less than evaporator pressure, what will happen? Here the pressure is higher inside the tube, and outside the pressure is lower. So what will happen? If there is a leakage, the inside refrigerant, it will flow out. So there will be a leakage of refrigerant. Okay. So in that case, so what they are saying, that suction pressure. Okay. So what they are saying, that higher suction pressure is needed. So that pressure of evaporator should be higher than this. So leakage of refrigerant, that we can avoid with the help of seals provided. But if there is a intrusion or infiltration of air and moisture, that we cannot control. Okay. Also, it adds some external pressure when the outside pressure is more than the inside pressure. Okay. So always remember that suction pressure or the evaporator pressure should be always greater than the atmospheric pressure. Okay. Now the second thing is discharge pressure, that is condenser pressure here. So at a given condenser temperature, the discharge pressure should be as small as possible to allow lightweight construction of compressor, condenser, and pipe. So what it is saying that, so we are talking here about the temperature dip. So whatever difference between these two levels. Okay, what they are saying, this evaporator pressure should be higher and the condenser pressure should be lower. In that case, what will happen? The displacement of compressor. Okay, so displacement of compressor depends on the pressure ratio. So as the pressure ratio is less will be the compressor displacement. Okay. So that is two properties, suction pressure and discharge pressure. Suction pressure should be more than atmosphere. Discharge pressure should be lower. In that case, what happens that compressor displacement becomes lower, and hence the construction of compressor becomes lightweight. Okay. Again, last lecture I have told you about the critical point. So what I told you, that the critical point of the refrigerant should be higher, because what is happening in critical point, that refrigerant will directly convert into vapor. So there will be no latent heat involved in the phase change operation. So we need that latent heat more, because we want to absorb the heat. So that is the purpose of refrigeration, to absorb the heat from the space. So for that case, we need this latent heat. Latent heat means the difference between, suppose I take here HF, that is enthalpy of saturated liquid, and if I here take, that is Hg. So whatever difference between Hg and HF, that is HFG, that should be more. So we need a larger latent heat for a refrigerant. So it should have higher critical point. Okay, so in this usual operation, it should not happen that it has reached to its critical point. So in that case, that whole objective of refrigeration becomes obsolete. And then I told you it should have low freezing point, because while operating, that refrigerant should not freeze. Okay, so it should not solidify, and it should not obstruct the flow. So in that case, that whole system will fail if the refrigerant becomes solid. So it should have low freezing point. Suppose your operation is in minus 30 to 20 degrees Celsius is your operating temperature. Its freezing point should be like minus 60, minus 70. Okay. So next we'll see pressure ratio, compression ratio. So in a system, uh, that pressure ratio should be as small as possible for high volumetric efficiency and low power consumption. So just now I told you that lower the pressure ratio, lower will be the displacement of compressor, higher will be the volumetric efficiency and lower power consumption. Latent heat of vaporization. So just now I have told you, I have showed in the figure that latent heat in the phase change should be as higher as possible, because we need to extract the heat from the space. So should be as large as possible, so that the required mass flow rate per unit cooling capacity will be small. So what you see on the screen here is an equation which relates this pressure ratio. Pressure ratio means this condenser pressure divided by the evaporator pressure, that is a pressure ratio, is equal to exponential. This is HFG. HFG I just showed you in the figure, that is a latent heat, divided by R. So R is its universal constant, into bracket 1 divided by TE, that is a evaporator temperature, minus 1 divided by TC, that is a condenser temperature. So what this expression says you that this pressure ratio, if I take pressure ratio as RP, is like directly proportional to HFG. Okay, is directly proportional to HFG. Okay, so what is happening here? If I want more latent heat, consequently this RP will also increase. So if I want more latent heat, pressure will ratio will also will be increased. But we have seen here that pressure ratio should be as small as possible. So this statement is contradictory. जर तुम्हाला latent heat जास्त पाहिजे असेल तर तुम्हाला pressure ratio देखील वाढवा लागेल. But theoretically speaking, we need a smaller pressure ratio. Okay, so what should we do? So there is a trade-off is required between the latent heat of vaporization and pressure ratio. So we have to adjust the value such that we'll get an optimal performance. Okay, so if you want to write, you can write. So I'll just go back to slide, previous slide. Okay, so if you want to make the note of this, you can make. Just write down the suction pressure. So just write down this last line, that higher the suction pressure is better, as it leads to smaller compressor displacement. And the discharge pressure, you can say that it should be as small as possible. Okay. Okay, so I'll move to the next slide. So write down that pressure ratio should be as small as possible and latent heat should be as large as possible. But according to that equation, these are like linearly proportional. I won't say linearly proportional; it is like directly proportional. So as latent heat will increase, that pressure ratio will also increase, or the pressure ratio will increase, that latent heat will also increase. So we want a trade-off between that, like optimum value of these two. Okay. So we'll see the next property. Next property is isentropic index of compression. So as we all know that if I'm going for a isentropic compression or expansion, so we have solved this example in chapter 1. So we have this PV raised to, suppose if I take 1.2 equal to constant, so we have this isentropic index of compression. Generally, if I am taking air, in the case of air, it is written as PV raised to gamma equal to 1 point equal to constant. So gamma for air is equal to 1.4. Okay, so this is your isentropic index of compression. So it should be as small as possible so that the temperature rise during the compression will be small. So whatever discharge temperature we are getting, so in compressor what is happening, at vapor refrigerant it is getting compressed. That means pressure is increased from evaporator pressure to condenser pressure. But as the pressure increases, its temperature will also increase. But if we look at the index of compression, if it is lower, then we'll get a lower value of the discharge temperature. So what it says, it should be as small as possible so that the temperature rise during the compression will be small. Okay. Next property we see, that is a liquid specific heat. So there are two fluids we are dealing here, liquid refrigerant and vapor refrigerant. So in case of liquid, that the specific heat should be lower, because when we are subcooling, that helps when we have lower specific heat, so that that is whatever temperature we are reducing, that we can control. So it should be lower so that lower heat will be absorbed per kg. So we'll see that should be as small as, so that the degree of subcooling will be large, leading to smaller amount of flash at evaporator inlet. So I'll explain you this statement. So what it's saying that the specific heat of liquid that should be smaller. So what happens? Specific heat means what? Kilojoule per kg. So that is a amount of heat per kg of the fluid. So if it is a less, what it means that per kg less heat will be absorbed or less heat will be released. So if it is a smaller, then subcooling, that is the cooling below the saturation temperature, that will be larger. That means if the saturation temperature is 100 degrees Celsius, so we can subcool up to like 50 to 60 degrees Celsius. So that subcooling, the difference between the saturation temperature and subcooled temperature, that will be larger. And it leads to smaller amount of flash at the evaporator inlet. So in last chapter, we have seen what is a flash gas. Flash gas is nothing but vapor refrigerant. So we have seen that we needed a liquid intercooling, liquid subcooling in case of multi-pressure system. Why we need liquid subcooling? Because we want subcooling of the refrigerant. Why? Because at the expansion wall, so expansion wall needs a liquid refrigerant. So that we have to remove that flash from the refrigerant. To remove the flash, we need a liquid subcooling. Okay. Now next is vapor specific heat, but this is contradictory in the case of vapor refrigerant. In this case, that specific heat should be larger. So what will happen? Large amount of heat will be absorbed per kg. So whatever superheating that we are getting, that degree of superheating will be smaller. Okay. So superheating, why it is unnecessary? See what is happening. Compressor works based on vapors. Okay, so it can work on saturated vapor also. If I go for superheating, like superheated vapor, in that case, compressor work increases. Okay, so that overall COP decreases because COP is equal to refrigeration effect divided by compressor work. So it should be large so that the degree of superheating will be small. So more the superheating, more will the compressor work. So that is why we need a larger specific vapor specific heat. Okay. So write down those specific heat. So liquid specific heat should be smaller and vapor specific heat should be higher. Okay, so we move towards the next property, that is thermal conductivity. So this you have studied in your subject heat and mass transfer. So you have studied in conduction that rate of heat transfer is directly proportional to rate of change of temperature. So Q is like directly proportional to dt by dt, temperature divided by time. Then what you are using, they are using a constant. That constant we are calling it as a thermal conductivity. So higher the thermal conductivity, better will be the or the higher will be the heat transfer. So thermal conductivity in both liquid as well as vapor phase should be high for higher heat transfer coefficient or higher heat transfers. Okay, so if you want to transfer the heat by conduction, more the thermal conductivity, that means that higher will be the heat transfer. Okay. Next property is viscosity. So this also you have studied in fluid mechanics. So when you are going for surface flows or a flow in pipe, in that case, viscosity plays a very major role. So we know that flow at the boundary, we are assuming it as a zero. And as we move away from the boundary, because of this viscosity, this velocity profile changes. Okay. So viscosity should be small in both liquids and vapor phases for smaller frictional pressure drops. So as the viscosity will increase, viscosity means it is a opposition to the flow. Okay, so more the viscosity, more it will oppose the flow, and that will create a pressure drop inside the evaporator or condenser coils. So viscosity should be small. Okay. So I'll just summarize whatever we have studied. So we are studying the thermophysical properties of a refrigerant. We started with suction pressure, discharge pressure. Then we here at pressure ratio, latent heat of vaporization. So that latent heat should be more. Isentropic index of compression, that should be lower. Liquid specific heat should be lower, but vapor specific heat should be higher. Thermal conductivity should be higher and viscosity should be lower. So I have that you have taken like small notes of this. Uh, okay, so when you study in details or in deep, or you will prepare your notes, that time this small notes will give a hint that we have studied this in our online lectures. Okay. So next we'll go to our second criteria of refrigerant selection, that is environmental. So environmental and safety properties. Give the title. Environmental and safety properties. So in contemporary times, environment friendliness of the refrigerant is a major factor in deciding its uses. So you cannot just directly invent any refrigerant which is very suitable for your refrigerant system, but which is very harmful for the environment. Okay. So first thing we are going to study under environmental, that is the ozone depletion potential. So see here we started with this. We started this lecture with like I asked you what is the significance of ozone layer, what is its use, and you have replied very well that it obstructs the passage of UV lights. UV lights are very harmful not only human beings but also agriculture crops. So we need to restrict its entry into our environment. So we have ozone layer at stratosphere. So as you know, we have studied this like in school days. What are the layers of atmosphere? So what we are living here, that is a troposphere. About troposphere lies up to 10 kilometers. After troposphere, we have stratosphere. So in stratosphere, we have this ozone layer. Okay. So this ozone layer deflects the UV rays, but what happens in ozone layer? This ozone gas. So generally, its molecular formula is O3. So O3, what happens? This UV light reacts with O3, and because of that, the ozone depletion may occur. But what is happening if I using refrigerant which are having chlorine or a bromine? So chlorine and bromine are having the largest potential to like destroy the ozone. So when this chlorine or bromine from the atmosphere it goes to ozone layer, that time what happens? These UV lights they react with this CFCs, that is a chlorofluorocarbons, and they separate the chlorine from these gases. Now this separated chlorine acts with the ozone. So there a reaction takes place between chlorine and this ozone. And that time another product is formed. That means it is destroying the ozone. It is said that one molecule of chlorine can destroy 1,000 molecules of ozone. And that rate of destruction is higher than rate of reproduction of ozone. So that is why it is very harmful. So in that Montreal summit, they have stop. They decided that we should stop the refrigerants which involve the percentage of chlorine. So according to the Montreal Protocol, the ODP, that is ozone depletion potential of refrigerant, should be zero. That is, there should be non-ozone depleting substance. Okay. But the question remains, what is the ozone depletion potential? How we can measure it? Okay, so what do you see on the right? That is the image of Earth, and what you see in the blue, that is the hole to the ozone layer. And this hole is above the Antarctic region. So generally it is called as Antarctic hole of ozone layer. So this is because of emission of greenhouse gases, and this gas is released from refrigerant industries. Okay. Refrigerants having non-zero ODP have either already been phased out, so R11, R12, so they were having a percentage of chlorine, so that is why they were phased out, or will be in near future, that is R22. So that will be also phased out because it is very harmful, or its ozone depletion potential is very high. Okay, so how they are measuring this ozone depletion potential? So they are comparing it with chlorine. So see, so since ODP, that is ozone depletion potential, depends mainly on the presence of chlorine or bromine in the molecules, refrigerants having either chlorine, that is CFCs, chlorofluorocarbon, or hydrochlorofluorocarbons, or bromine cannot be used under new regulations. Okay. So we'll see that uh, about this greenhouse gases and ozone depletion potential. So chlorine is having the highest ozone depletion potential. So other refrigerants will be compared with this chlorine, that CFCs, and they will decide what is the ozone depletion potential of the refrigerant. Okay. So for a base, they are using CFC, chlorofluorocarbon. So they first will calculate what is the ozone depletion potential. Like they will take suppose 1 kg of CFC, and they will observe that how much amount of ozone is being destructed. So that will be its ozone depletion potential. Then if I take a reference refrigerant, so I will take a reference refrigerant, so which I have produced in a laboratory. I will compare its ozone depletion potential with the help of CFC's ozone depletion potential. So whatever this ratio we are getting, so that will be the assigned to this reference refrigerant. Okay, so CFC, that is our base element here, will calculate for CFC, and this will be used to compare the ozone depletion potential of any new refrigerant that will produce. Okay, so in here under environmental, this was our first criteria, that is ozone depletion potential. Not only our refrigerants, there are other gases in the environment which are harmful for the, or which are responsible for the ozone depletion. Next criteria under environmental, that is global warming potential. Okay, so first was ozone depletion potential, second is global warming potential. So we are aware of various greenhouses like CO2 is there, then methane is there, then nitrous oxides are there. So these all what they do, they trap the heat in Earth's atmosphere. So as they are trapping the heat, and because of that, Earth temperature rises. So that temperature rise, what we are referring it as a global warming. So what you see figure on the right, that gives you the percentage of industries which are responsible for greenhouse emissions. So you see that electricity sector, that is a power sector, has the largest, or is the most responsible for the emission of greenhouse gases. It is followed by transportation, that is automobile industries, the industries, then commercial and residential, and the least is agriculture. So agriculture sector uh, gives least emission of greenhouse gases. Okay, so that global warming potential or GWP, GWP is the heat absorbed by any greenhouse gas in the atmosphere as a multiple of heat that would be absorbed by the same mass of carbon dioxide. So what it means that they are first calculating how much amount of heat is absorbed by CO2. So this will be our base. First, we'll calculate how much amount of heat is being absorbed. Let us say per ton, 1 ton of CO2. Then we'll calculate how much of amount of heat is absorbed by another greenhouse gas. If I take the ratio of it, so that will be my that will be my global warming potential. So obviously, refrigerant should have as low as a GWP value as possible to minimize global warming. Okay. So in next slide, I will show you that table of GWP. In that, your ideas will be more clear about this global warming potential. Refrigerants with zero ODP but a high value of GWP, that is R134A, are likely to be regulated in future. So it should have low GWP. Also, it should have zero ODP. Okay, zero ODP should be zero, but at GWP, we cannot make it zero. So that should be as low as possible. Okay, so I'll just show you that table. Then we can go for another term. So here, what you see on the screen, GHG means this is a greenhouse gas. Okay, and this is a global warming potential for the span of next 100 years. Okay, the CO2 is our reference gas. Its GWP is obviously 1. It is the same as like specific gravity we are taking, and we are taking water as a reference in specific gravity. So similarly here for this GWP, we are taking CO2 as a reference. So next in that is the CH4. So CH4's GWP is 23. Now what this means that CH4 has the ability to create a thermal impact 23 times more than CO2. Okay. Now next is N2O. So it has a global warming potential of 296. So that means that it has the ability to create a thermal impact 296 times of CO2. So if you go here, HFC, it has 12,000 GWP, SF6 that is having 22,200 GWP. So our effort should be to minimize the GWP, and that ODP, ozone depletion potential, should be 0. Okay. So this is all about GWP. Then next term under environmental, we have that is a total equivalent warming index. So this term is specifically used for refrigerant, that is a TWI. It is also called a TV, TWEVWWE. Okay. So total equivalent warming index. So what they are doing in this case, they are taking into account the direct effect of refrigerant. So suppose from a refrigeration system, a refrigerant is leaked into environment, and that is called some damage to the environment. Second thing they are accounting, that is a indirect effect. Indirect means if I'm operating a refrigeration system, definitely I will need electricity. Why I will need electricity? To drive the compressor. Compressor drive करायला मला electricity लागणार आहे. आता बघा, most of the electricity in our India is generated through thermal power stations. And this thermal power station, they work on coal. तर त्यामुळे मला coal burn करावं लागतं, आणि in that burning process, or in that huge boiler or that burner furnace is there, that furnace CO2 is emitted. म्हणजे काय झालं की माझ्या एसीला लागते इलेक्ट्रिसिटी, ती कुठून येते? थर्मल पॉवर स्टेशन. थर्मल पॉवर स्टेशन मध्ये काय होतंय? CO2 तयार होतंय. सो दॅट विल बी ऑल्सो इनडायरेक्टली अकाउंटेड अंडर टोटल इक्विव्हॅलेंट वॉर्मिंग इंडेक्स. Okay. So the factor TWI considers both direct due to release into atmosphere, and indirect through energy consumption, contributions of refrigerant to global warming. So naturally, refrigerants with as low a value of TWI are preferable from global warming point of view. Okay, so that table also I will show you. So naturally, the refrigerant should have a low value of TWI. They also should have a lower value of GWP. Okay, so this is the the formula. If I'm going for TWI, that is a total equivalent warming index. So TWI. Okay. So what it is considering? It is considering the direct effects. So if a refrigerant is leaked through a system and it will go into the atmosphere, it will do a damage. It is also considering the indirect. So whatever electricity we are getting, in that case, some coal will be burned and that burning process CO2 will be generated. So that will be also accounted under indirect GWP. Okay. So this will be indirect. So what you see formula here, what they are doing, this GWP direct, they are multiplying it by refrigerant mass, then L means leakage and into N. N is the life of the system. Okay. So if I'm considering a refrigerator I have taken for 10 years, so I can easily calculate how much mass of refrigerant is present inside the my refrigerator. What is the leakage rate per year? And if I take 10 years of life of my refrigerator. And if I know that refrigerants GWP from the catalog, easily I can calculate this direct impact. Okay, so this is about direct impact. If I go for indirect impact, in this case, again, GWP of the refrigerant, mass of the refrigerant, then they are considering some recovery factor. Then they are considering the energy generation or energy consumption, then some factors, and then the service life of the plant. So if I take a thermal power plant, it is generating power in like suppose k kilowatt hour, and for this kilowatt hour, some ton of refrigerant will be used. So I will use calculate this for a year on a yearly basis. And from that, I can calculate the mass, and then I can multiply by GWP. Then I will get the indirect contribution. So this way they are calculating the TWI. So TWI is specifically used for refrigerant, but that global warming potential GWP is used for any gas. Okay. So I'll give some time to write it, 2 minutes, and then we'll stop today. Okay. So start with this ozone depletion potential. Okay. Write about the global warming potential and total equivalent warming index. So just write some short notes so that while revising or while you do your detailed study, write your notes. That time you don't have to study again. Okay, so you can refer to these short notes and then you can get the idea. And also this knowledge is not limited to only our subject, that is the refrigeration and air conditioning. These terms like ozone depletion or global warming, these are applicable like other subjects also. If I consider environmental issues, if I take energy efficiency, in that case also you can use, or this concept will be used. Okay, so whatever figure you see here on the right, that is a pie chart for the contribution of sectors in production of greenhouse gases. So largest contribution is of electricity or power sector, and least is agriculture sector. Okay, so time is over. In next lecture, yes, I will revise these things, and we can continue our this chapter. So quickly, I will take the attendance, and then we can stop. So please bear with me while I take the attendance.